Hello, GW. So I'm so glad to have the opportunity to present this information to your class, Mary, today at GW. I had originally created this presentation for a Department of Energy conference on solid-state lighting, a research and development conference in 2017. And we're very specifically trying to answer the question, how to select a spectrum of light to reduce the risk to museum collections. And I was part of a panel where we're talking about spectrum and how do we manipulate the spectrum of light for specific applications. Because now we have LEDs, these solid state lights, and we can manipulate spectrum like crazy, and we can do almost anything. What do we want to do? And let's talk about it. This is my old test bed full of different color LEDs. This speaks to the problem of there are so many choices of LEDs. These are mostly light bulbs. Now there's tons of different types of fixtures. How do we choose among them? And how do we say this light bulb might be better than that light bulb? To answer the question for damage, we're going to attack that today. At the Smithsonian American Art Museum and the Renwick Gallery, we looked at this problem every which way we could, both aesthetically and damaging. For aesthetics, to see, does the new LED technology match the old one? I reached out to the US Department of Energy, and we did studies together, and we wrote those studies up. I also had access to the National Institute of Standards and Technology in Gaithersburg. This was fantastic. To have access to all of these lighting scientists to help us in our work was extraordinary. And again, we wrote those results up with the help of the Department of Energy. To determine how LEDs damage light-sensitive materials, we leaned heavily on these two gentlemen, Jim Druzik, who was at the Getty at the time, and Stephen Weintraub. And I'm eternally grateful to all of these men and women. Wendy Davis was at NIST. She spent hours with me in the NIST lab, and she subsequently went off to the University of Sydney in Australia. We then also wrote up our results as part of a recommended practice for the Illuminating Engineering Society. What causes photochemical damage? Photochemical damage is what's primarily responsible for light damage in art museums. What you're seeing here is a list. I'm pulling it straight from both the recommended practice from IES and from a previous document, CIE, which is the International Lighting Organization, 157-2004. And that document lays them out both as far as what we do as museum people to reduce damage, as well as a process. The first is the light-sensitive material. That's selected by a conservator who will tell us, is this object more light-sensitive than another object? We then talk about the intensity of light, IR and UV. IR and UV are very easy to filter, so we're largely talking about light. The duration of exposure, how long is that light on? And lastly, and I'd say least importantly, a spectrum of lighting source, because after you've gotten rid of the IR spectrum and the UV spectrum, what you're left with is light. For those that have heard it before, this may be a repeat, but it's worth hearing twice, and I'll move quickly through these basic ideas. That the lighting levels that we have selected for museums, these are the most common standards of 50 lux for very light-sensitive materials. And for things that are more durable, like oils and acrylics, a more optimum quantity of light, 200 lux. These were chosen as minimal quantities of light we need to enjoy materials. And of course, the difference is that 50 lux, something that might last a year and a half, we can increase the quantity 4 times, and it can last 50 times longer if the material is more durable to light. Duration of exposure, if things are being lit when people aren't in the room, you're damaging it for no reason. We really try to reduce the duration to minimum amounts possible within the relative constraints of everything we're working with. Last is the spectrum of the lighting source. Let's do a dive into that. That's really the topic today. Even though, again, it may not be the most important thing, it really will help us decide, is this LED more or less damaging than another LED? What you see on the screen is a power spectral distribution of an LED. When the x-axis is the rainbow, Roy G. Biv from red to violet on the x-axis, showing that as you move along the spectrum towards ultraviolet, that the light becomes more energetic, that this is going to create more photochemical damage and more photochemical reactions than the red side of the spectrum or the ultra-infrared side of the spectrum, which is measured in heat. At least that's how we typically measure it within our context. And in the middle, we get light. The fancy shape in the middle is an LED, and it's a blue pump phosphor LED is what we call it, with the blue LED at 450 nanometers and the phosphor over here. Let me show you what I think is a cool example of this. I had a scientist working with me from the Pacific Northwest National Labs, Michael Poplawski, and we were looking at this light bulb. It was actually just a light bulb in my hands, not in a white void, and we smashed it. We subsequently cut ourselves and bled. After we mopped up and bandaged ourselves up, we saw that there was two elements, that there was this LED module, which was a blue LED, and this disc, which was a silicone disc with phosphor embedded into it, and that when we held the phosphor up to the blue LED, it glowed white. Let me show you. There you go. I'm being lit blue. You see the blue LED that we smashed, and that silicone disc embedded with phosphor. And you see how it's white? As I bring it closer to the blue LED, it explodes in light. You can still see that there's blue in the background until finally, when I completely cover the blue LED with the phosphor disc, I get a nice white light. And on the background, you see a color checker that will give me a reference of how well I'm seeing color. And that's an assessment, that's a good use of these spectra. Some people think that you can assess the quality aesthetically of light by looking at these spectra, and I'm here to tell you, you can only tell minimal amounts about the quality, the visible quality of light from a spectral power distribution. These are measurements of energy, and that's the way you should look at them. There's a couple different ways to create what we call white light. There's blue pump phosphors, which I just showed you, and they're most common. Violet pump phosphors also are out there, and you'll see them in museum applications. And there are UV pump LEDs. These should not be in museum. They're very rare, but you need to make sure that you're preferably using a blue pump source or potentially a violet pump source. There are other ways to create white light. There are multicolor LEDs. At the most minimum, red, blue, and green, it's not going to give you very good color rendering. Most optimally, any number of these. I'd say these bottom three are where you're most likely to get good quality results. Again, don't look at these spectral power distributions and see if you can assess quality. It's beyond the scope of today's talk, but this is showing you TM30, which is an assessment of color rendering quality. And it shows that if this circle is complete, that it's very good color rendering, and that this continuous spectrum incandescent light, shows right there incandescent, is equal to this very discontinuous spectrum LED source, in this case a red, green, blue, amber source, that both of them provide excellent color rendering, even though they are very different spectra. And there's slightly different Kelvin temperature, which is why that black curve is a little bit different. I could just as easily have created a lighting source which is exactly the same and is the same Kelvin temperature. Methods for selecting a spectrum of light to reduce risk to museum collections. That is why we're here today. There are two main ways of doing this, two different methodologies, and we are going to discuss both of them. One of them is spectral damage function, SDF, and the other is action spectra. First, let's take a look at spectral damage function. And we're going to take another look at that graph we saw again. X-axis is wavelength and spectral power on the y-axis. We're looking at, again, a blue pump phosphor lamp, now without a pretty rainbow, because on top of this, I'm going to layer a damage function. The red line you see that just popped up, oh, and now we've got green lines. The red line is the first damage function that was created in the 1950s when fluorescence started becoming popular, and specifically it was a team study between the National Bureau of Standards, which would become NIST, the National Institute of Technology, where we've got great light scientists and color scientists and vision scientists that are studying what the lumen is and how we see, and other aspects like how things get damaged. They were in partnership with the Metropolitan Museum of Art, and specifically a conservator, Harrison, who together they saw that the primary cause of damage, and they were only studying one material, high acid paper, newsprint, and they saw that most of the damage from newsprint is happening within the ultraviolet. And this is where we get this kind of rumor that ultraviolet is, once you've filtered ultraviolet, that you're not damaging the artwork. That is not true. Of course, you also have to control the intensity of light. Leap forwards about 30 years to the German laboratory of Krachmann and Ayalinde. They created the curves you see here in green, and they measured all kinds of things on different substrates, on paper, on a canvas, and they saw that indeed the spectrum of light is continually damaging well into the visible spectrum. This is extremely useful information. I got a material scientist, Masahiro Toya, and the two of us in partnership developed a calculator. And if you follow this link here, you'll be asked to fill out a short form, and you will then have access to this calculator. Joe Padfield also provides a publicly available calculator at the National Gallery, along with some wonderful information. And this is what the calculator I developed looked like. Very briefly, you saw the red and green curves. The blue lines, in this case, is a fluorescent that I was measuring. The yellow curve is human vision, which is peaked at 550 in the 5 nanometers. When you look at a lumen, it's largely a measure of this green-yellow energy peaking at 550 in 5 nanometers. And it'll give you absolute values, but the calculator also gives you the opportunity to show how one lighting source is relative to another lighting source. And I'll show you those calculations in a few minutes. I also wanted to show you this page out of David Saunders' recent book, Museum Lighting, A Guide for Conservators and Curators. And it's a wonderful book where he has illustrations that I don't understand because, of course, I'm a lighting designer. And once you get to this level of chemistry, this requires a conservator or a conservation scientist or a material scientist. But my understanding is that some ultraviolet light is needed to break a lot of the polymer bonds for a lot of materials. But yet you see that there are some common bonds that can be broken with invisible light. Please consult a conservator, a qualified conservator or conservation scientist to assess your specific material needs. And buy David Saunders' book. That's using action spectra. That's going to give you an answer, and a very general answer about action spectra. It's not going to solve all your problems. Let me tell you why. because I'm sorry, we just talked about spectral damage function. That's going to give you some general answers. Action spectra will give you specific answers. The action spectra here is, again, many thanks to David Saunders, who, with Kirby, published this in 1994, and then Kit Cuttle and Neiman reproduced it in CIE 157, 2004, where they're seeing how specific things will fade. It's a very different question than how just assessing the short length action on largely these polymer bonds is my understanding. So let's take a look at a specific one. Let's say this litmus blue. The damage function, that generalized spectral damage function, is here, which is largely assessing short wavelength energy. But this is a blue object. And what it's saying is the damage action spectra of this particular blue is actually less active in the blue region and more active in the red region. And that makes sense because what is primarily responsible for damaging materials, and if the rest of the conversation has been complicated, this is going to be in English. If light hits a blue square like you see on the screen, it is the light that is absorbed by the blue square that is largely going to be responsible for damaging organic dyes and pigments. So the absorption spectrum, what is absorbed over that blue, you can see matches the shape of the action spectra. And that these curves for action spectra, the actual energy required to fade a piece of blue litmus is very different than the generalized spectral damage function. So both of those curves, whether it's specific action curves for specific materials or the generalized spectral damage function, are very different than what we call the luminosity function. The luminosity function is the lumen. It's how human beings see. When you measure a foot candle, that's lumen per square foot, or lux, a lumen per square area. Kit Cuttle tells me that there's nothing in the world that has an action spectra that's similar to the lumen, yet in museums, we use the lumen to assess damage all over the place. And that's largely because all of this is too damn complicated, and using a vision-based system of using the smallest amount of lights we need to see is the best we can do to deal with the complexity of managing our damage on our artworks. It's uncomfortable to hear that science is just too complicated, and we're relying on our human visual system, that we want to use 50 to 75 lux, typically on very light sensitive things, and 200 lux on more durable things. So we've got these two mechanisms. Let me go through it. Spectral damage function is general. It can't predict damage to specific objects. The fancy way of saying that is it doesn't predict post-irradiance effects. It's useful for assessing a light source's damage potential to a group of objects. In other words, it can help us pick a light bulb and say for a generalized group of objects, is this light bulb more or less damaging than that light bulb? It does have utility, and I'll show you examples of that in a minute. Very important that it's quaternary in importance, or quaternary or septenarian, after the most important. Make the light dimmer, reduce the duration and exposure, and eliminate infrared and ultraviolet. That is of the utmost importance. And all of this fine-tuning of the spectra, which a lot of people want to do because now we can with LEDs, it's really way down the list of importance. And lastly, pigments in the low light sensitivity category are most susceptible to short wavelength damage. And this gets into minutia, and I'll get to that in a minute. Action spectra. The action spectra is specific for a specific material. It can be used to predict fading of specific objects. It requires spectroscopy to determine precisely what pigments and dyes exist in the material, and it is not commonly used because it's so complicated and time consuming, and it requires special equipment and scientists to do well, or perhaps very well-trained conservators. And our conservation community is extraordinary, and there are conservators that are so tenacious that they're going there and they're going to figure it out, and I'm grateful for their help. On the left where it says pigments in the low light sensitive category, that means that the pigments and dyes that are most susceptible to this short wavelength energy, ultraviolet and things that are near UV, are more likely to be actually a little bit more durable. And materials that are closer, that are very light sensitive, are actually a little bit more broadly responsive to the entire spectrum. I went off and I measured a bunch of lights, and I wanted to show you my data. And that will give you a little bit more information about how to use these metrics in real life. I normalized the data to my halogen lights. I normalized it as a 3000 Kelvin halogen, and that's a damage factor of 1. My blue pump phosphor LED in yellow, so a typical LED with good CRI, with substantially less damaging using spectral damage function than my halogen light, roughly 23% less damaging. And if I compare that to a violet pump LED, which is popular, that's slightly more damaging lumen, wavelength per wavelength than halogen. My results were reconfirmed by Michael Royer at the Pacific Northwest National Labs, who saw, hey, listen, if you take a general class of lighting sources, the blue line is LEDs, that as a class, as you get cooler and cooler, meaning that as the Kelvin temperature increases, the typical ones that we use for museums are often at 3000 K, daylight is closer to 6000 K, that the damage increases as we increase how cool or blue the light is. And that increases as a trend depending on the technology. So fluorescent is up here, and fluorescents as a group will get cooler as they get cooler and cooler, and so forth. On the x-axis is Kelvin temperature, and on the y-axis is relative material damage. Again, I tried something else, which is, well, how about those like discontinuous spectrum? Again, I start with the halogen lamp, and now I'm using a red, green, blue, white LED with a very discontinuous spectrum. But if you measure the area below, you can see that there's actually less energy in the LED, and indeed, it's significantly less damaging per wavelength, even though you see these giant weird spikes. There was some false information that went out many years ago that says, hey, when you see these spikes, danger, do not use. That information turned out to be completely wrong. And the spectral damage function that I've been talking about is the correct way to assess the potential for damage. And lastly, if you take a look at another more continuous spectrum LED with a higher color rendering, that it actually also is a little bit more damaging, and that there's no relationship between color rendering, which is what these metrics are, R of F, as compared to damage. Again, Michael Royer reconfirmed these results in his document True Colors, where on the y-axis, he's plotting damage, and you can see that there's straight lines across. Where color rendering, as you get better and better color rendering, that there's no relationship between color rendering and the amount of damage, but there is a relationship between the color of light and damage, with warmer lights being less damaging than cooler lights, which is what I was saying, that daylight is likely to be more damaging lumen per lumen than warm electric light. Again, my spreadsheet can help this. assess your own lights. You can input your own spectra if you have them available. And there are lots of test spectra within the different tabs on the Excel spreadsheet. And Joe Padfield also made available many samples on his website as well. Within the question and answer question from the George Washington students, I wasn't allowed to record that because, you know, there's some liability trying to get students on record. One student asked a particularly good question, which was, how do we know exactly how things are fading on a specific artwork? And I wanted to show this slide. This, first of all, shows the whole problem, that there is always three things that we're assessing when we're looking at lighting. There's always a thing we're looking at, in this case, art. There's something receiving it, which is a person. A standard receiver is the spectrum that we're seeing here, and light. And that for vision, we're integrating all three of these. If we're trying to answer the question, how much is a specific artwork being damaged, we can measure a particular point, which really needs to be done in a laboratory with the artwork flat. That is extremely difficult to do. And it is actually very rare that people are doing what you're seeing here, which is measuring with a spectrometer a specific color of a painting. In this case, intern Carey, many years ago, was measuring the blue of the Marsden Hartley. First, he holds it up to a white standard, and then to the blue of the canvas. These peaks are noise, and what we're seeing is that, yes, this is blue. And whether you're measuring it just as energy with this kind of fake rendering of blue within the spectrum, or you're integrating with human vision, it's blue. But the secret of museums is we really don't know exactly how things are fading. Good conservators and conservation scientists can do it, but the work is too great, and we haven't streamlined it. So we can't, and we don't have good pre-exposure data on most of the artworks in our collection. I hope that the current practice will be seen as barbaric in the future, because the current practice is to put things out on view, light them reasonably dimly at 50 or 200 lux, and hope that they don't change. And then take them off view when we're afraid that they might change. I understand why we do this, and we do this for the best of reasons, and it's the recommended practice for a reason. But I hope in the future we can actually do a better job measuring the pristine condition of the artwork before exposure, so we have more of a sense of what we're doing over time. And that is what I have prepared to help our museums choose the least damaging light bulbs, help us see better, hopefully, and make these difficult choices.